Hey everybody. So we're going to start this video with some nonsense. Take a look at what I've written here. Okay, so I'm looking at an integral where my upper limit is infinite. I'm looking at the function 2 to the negative x, right? So 1 over 2 to the x, another way to write that. And here's a picture of this, of the graph of this function. We're just looking at it from 1 to infinity, well, up to about 10 here, but it just keeps going on, right? So I have to decide what I mean by this symbol, okay, right? Infinity is not a number, so even just writing this demands some explanation. But the maybe obvious interpretation is what I'm asking is, what's the area under this curve if I start looking at the area starting at 1 and going on forever, right? And so if we keep going forever, you might suspect there's an obvious answer. And I would not fault you for this, right? I mean, if you're adding up, if you're looking at an area that goes on forever, even though it's getting, right, this graph is getting increasingly, the height of this graph is getting ever closer to 0, it's still going on for area. So let's first see if we can justify that this should even have a number, right? That's where I'm going with this. I actually want to compute this. So I didn't write this here just to say these don't work. This is actually, we're going to decide some kind of meaning to all of this. And I want to start with something maybe a little less complicated than an integral. That word disappeared for a moment. So I'm going to add something to this picture, okay? I've created these rectangles. Notice each rectangle is 1 unit wide, and the height, this looks very much like when we created areas of integrals. This would be these left-hand rectangles that we did at the very beginning of these videos. So let's look at this first one. Its width is 1, its height is 1/2. So that rectangle has an area of 1/2. The next rectangle still has a width of 1, but it only goes up to 1/4. We're just going to the next value of x, right? This is the x, the 1/2 was where x equals 1. When x equals 2, the height is 1/4. The next one will be 1/8, and on and on and on, right? If we go out to the 50th, would have 1 over 2 to the 50th, and on and on and on. So this just means n is just all of the positive integers, okay? So now I've got something that I claim is simpler than an integral, which is an infinite sum. I'm asking you to add up these numbers forever. This is also something that isn't obvious, should have an answer. But let's do this. Let's assume that this does have an answer. Let's decide what this answer should be. And I'm going to do this visually, I think. Let's put a number line out for ourselves. So let's do it like this. Here's a number line. And let's just put 2 numbers on it. Let's have 0 and 1. Okay? So what I want to do is visually represent this sum as we go down the line, right? When I add the first number, I get to 1/2. Right? When I add 1/2 plus 1/4, let's think about what we're doing. If I start at 1/2, to get to 1 would be, well, let's just add 1/2 and 1/4. That gives us 3/4. So now I'm out here. Maybe it looks better like this. Okay? So I get out to 3/4. Then I add 1/8. All right, adding 1/8 to 3/4. 3/4 is 6/8. Adding 1/8, we get to 7/8. Okay? So what's the pattern here? I started at 0. I got halfway to 1. Then when I added 1/4, I cut the distance left to 1 in half, right? At this point, I'm half a unit away from 1, right? Right here, we're half a unit away from 1. Here, we're 1/4 of a unit away. Here, we're 1/8 of a unit away. If I added the next one, I would get, so the next one in this series would be 1/16. I would get up to 15/16, then 31/32, then 63/64, right? So each time I add another number, I'm cutting half the distance from 1, okay? If we think of these sums as a location on this number line, which is a good geometric way to think of it, I think. So what does that mean? If there is a sum, here's a couple of things. If this infinite sum equals something, let's just call it S, I'm going to argue, first of all, that S can't be greater than 1. Right? So there's my greater than symbol with a slash through it. This can't be true. It can't be greater than 1. Right? Because we're just, as we see in this pattern, no matter how many times we add, all we ever do, if we zoomed in again, I could keep cutting this distance in half. I'm only ever getting a half a unit closer to 1. So I'm never going to get past it. On the other hand, the distance or the sum can't be less than 1. Because if I pick a point here, let's say I claim it's less than 1, then it's got to be some number. Well, at some point, if I cut that distance in half enough times, I'll get closer than that, right? If I say, well, it's 0.99. Well, eventually my distance from 1 is going to be less than 0.01. In other words, I'm going to be bigger than 0.99. So any number you can pick that you want to be the sum that's less than 1 won't work, because I can show you precisely the moment in this sum where we get bigger than it. We're always going to get bigger than it if it's something less than 1. Well, what does that leave? The only possibility left is that the sum is 1. Okay. Now, I haven't proven that it should have a sum. Right? There's no reason, obvious reason to say this has to add up to something. But I think I've argued that if you're going to have a sum, the sum should be 1, because we know it can't get bigger than 1. We know that any number less than 1 will eventually get past it, so that only leaves one option. Okay? Well, it turns out it's useful for us to have sums like this, right? And useful here means it helps us perform mathematics, which helps us do things in the real world. And so because it's useful to have this sum, there's other arguments to be made. I think that's a pretty good one. The sum is going to be 1. All right. Now, why did I just do all that? Look at my picture. The picture shows that the area under this curve is smaller than the area of these rectangles. And we just decided that the area of these rectangles, even though they go on forever, if there's going to be an area, right, we did it as sums, but that sum is the same as adding up the areas of these rectangles, is 1. And geometrically, what we see here is that this integral is less than this sum, which we just decided, or maybe I just decided, if it's going to have an answer, has to be 1. And so the area of this integral, now it's a little more reasonable to think, even though that area goes on forever, that little strip at the bottom of this graph just keeps going and going, right, as we go out to infinity, somehow, in the same way that somehow these numbers keep adding up forever, but they never get past 1, that there's an area that we can make sense of here. Okay, so here's what I'm going to do. Let's do some computations. Let's start computing some areas. Okay, so let's take a look at, let's just do the integral from 1 to 10 of this 2 to the negative x dx. Right, so just looking at, in fact, I can give us a picture of this. Let's go back here. Let's turn off the rectangles now. And here's the area from 1 to 10. Maybe I'll take this picture out a little bit. Let's go up to 20. Right, so we're looking at the area up to 10. So this shaded area that I have right here, okay? So if I compute that area, the antiderivative of 2 to the negative x is going to be negative 1 over the natural log of 2 times 2 to the negative x, and we're evaluating it from 1 to 10. So this is negative 1 natural log of 2, 2 to the negative 10 minus 2 to the negative 1, which is approximately, and I'm going to write a lot of decimals here for a reason we'll see in a moment. This is 0.71993863 8569. All right, well, why don't we go out 10 times farther? Let's go out to 100. 2 to the negative x dx. Same antiderivative. Negative 1 over natural log of 2. 2 to the negative 100 minus 2 to the negative 1. Plug that into a calculator. This is approximately 0.721347 520445. Okay. And I think that's right. I think I may have inverted these. Let me switch this to, this one should have been 4. Right? Yeah. All right, one more. Now let's go out to 1,000. 2 to the negative 1 dx equals negative 1 over the natural log of 2 times 2 to the negative x, 1 to 1,000. We get negative 1 over the natural log of 2, 2 to the negative 1,000 minus 2 to the negative 1. And now we get 0.7213475204445, I believe. Okay, those are decimal approximations, but we see a couple of things. First of all, notice when we go out to 10, we have really close to 0.72. We're just a little bit below it. When I extend this graph, let's go out to 2,000, right? Well, what happens? This function 2 to the negative x, right? So all that area in the beginning is now in this little tiny sliver on the left side. This function gets really close to 0 really fast, right? So we're adding up all this area out here, but it's not really adding that much because when we go from 1 to 10, we're already at almost 0.72. By the time we go out to 1,000, we've gotten just barely above 0.72. So in those 9,990 units of area, there's very little area actually there because the graph is so close to the x-axis, right? Okay, so the other thing we should notice is that this became very tedious very quickly. I'm doing the same thing over and over again, right? Each time I have the same antiderivative. All I did was add a 0 to the upper bound and recompute it, right? It seems silly to go through this whole process over and over again. So maybe, we'll use this graph a little later, so let me just move this guy down. Oops. Button. So maybe what I could do is instead let some letter, some symbol represent whatever upper bound I'm going to have. So I could streamline this whole process by doing the following. Let's just compute the integral from 1 to t, 2 to the negative x dx, right? I'm just putting in t for the upper bound because all I'm doing is whatever the upper bound is, I'm just changing that here. So I go through this whole process each time. If I want to do 10,000 or a billion, I don't need to do all the same work again. I see where that billion is going to end up. So this will look like negative 1 over natural log of 2. And it will be 2 to the negative x from 1 to t, which will look like negative 1 over the natural log of 2, 2 to the negative t minus 2 to the negative 1. Okay? All right. Well, look at what we were doing. We were making the upper bound that I'm letting t represent the upper bound. As what I want to do is keep taking values higher and higher and higher and seeing what happens to the sum. We've already seen a little bit of what's happening. It's getting close to this number 0.72 something, right? It's changing very little the further we go on because most of the area happens in the beginning, and then there's all these little tiny pieces to capture as we go further and further out. But if I look at this algebraic expression on the left here, what I'm doing is making this t larger and larger and larger, right? So remember, 2 to the negative t just equals 1 over 2 to the t. What happens to something like this as you make t larger and larger and larger? Your denominator gets larger and larger and larger, and that fraction gets smaller and smaller and smaller. In other words, this piece, this 2 to the negative t, becomes increasingly insignificant. The further out we go, the less this little subtraction piece matters, right? It's 1 over 2 to the 1 billionth, right? It's an incredibly, unfathomably small fraction, right? And we can go even further. In other words, this piece nearly disappears. So what does that mean? Let's get this out of the way. What does that mean? Well, as we go on, as we get further and further and further, as t gets larger and larger, this piece barely matters anymore. We get negative 1, something very close to which we can rewrite this as, look at this as a negative 1/2. We've got two negatives, we've got a 1/2, and we've got this expression. Okay? What did we just do? We just took a limit, right? I just talked through the idea of a limit as t goes to infinity. As t goes to infinity, this piece becomes increasingly insignificant. In other words, the way I just computed, well, I guess I haven't said that I computed it, but what we're saying here that is as t gets larger and larger and larger, the values that are going to pop out of this, of these integrals are getting closer and closer and closer to this number, 1/2 natural log of 2, which is pretty close to this 0.72, etc., right? Depending on how powerful your calculator is, you can get better and better approximations to that number, okay? In other words, we're taking a limit, and we can use that as the sum of this integral, right? It's really the same thing I did here. All this arguing I made about the sum is always going to get bigger than any number smaller than 1, but it's always going to be, it can never be above 1, is a long way of talking about limits, okay? These are all limits we're really talking about. We know that we're never going to get done adding up these infinite numbers and get to 1. Just like there's no number I can put in for this upper bound so that the calculation here is exactly 1/2 natural log of 2. But what I know from this computation and this thinking is I can get as close as I want to this number by making t larger and larger. If you want me to be 1/trillionth away from this number, 1/2 natural log of 2, I just have to make t very, very large, right? And you can do some computations to see how large you'd have to make it. As long as this thing is smaller than 1/trillionth, then the thing we're subtracting, well, that's not quite true because it's multiplying, but it's not a terribly difficult computation. Just make t really, really big, this number's really small, and we'll be really close to this. In other words, what we did to compute this integral we took the limit as t went to infinity of this integral, where t was standing in for the upper bound. So we did the integral first, right? That's what I did here. Here's my integral. And then I took the limit, right? I didn't use the limit symbol in here. We just kind of talked our way through it, but that's where I took the limit, talking about this thing getting smaller and smaller and smaller. And so this is how we're going to define these kind of integrals. They're going to be defined as limits, all right? So let me make this our definition clear, and then we'll do a couple more examples, all right? So let's just put up a little division here. All right. Again, we're going to come to this graph in just a few minutes. Let's just move it down for now. That's for our examples later. All right, here's our definition. We call these improper integrals. And we're not going to get into this video, but there is a different kind of improper integral. So if you've seen these before and wondering why I haven't talked about that one yet, I'm going to save that for another video. It's similar idea, but a little bit different. So for now, we're just looking at this type, which I'll define down here, the type we're talking about. Improper integrals, and I'm going to use a and b are constants, or are real numbers. Okay. So there's going to be three statements I make here. If, let's see, we have to say a to t f of x dx exists for all t greater than or equal to a, then, oops, that says them. Let's do this right. Then the integral from a to infinity f of x is defined to be the limit as t goes to infinity provided this exists, the limit exists. All right, so what we're saying is just what we did above. To compute this kind of infinite integral, right? A in our example was a 1. If we're taking integral from any constant, though, it could be negative a billion, it could be 10,000, up to infinity. What we do instead is we put in a symbol, t usually, but any symbol will do, for some large number, and we take the integral for that large number, and then we imagine limit. We imagine what happens as that number gets larger and larger and larger, okay? Notice two things. This doesn't always have to exist, and we'll do an example where it doesn't. And also that this function has to exist for all t greater than a. So for instance, if somewhere out there we have like an asymptote or a hole in our function, things can go wrong with this. So you need a function. You know, continuity is a good standard. That's typically going to be enough, though there can be some cases essentially that it would work regardless. But continuity is a pretty good mark for us. Really what we want to watch out are things like asymptotes, right? If there's an asymptote out there that can throw this thing, a vertical asymptote that could throw this thing off. All right. We can do the same thing in the negative direction. If the integral from t to b, f of x dx, exists for all t less than or equal to b, then the integral from b to negative infinity, f of x dx, is equal to the limit as t goes to negative infinity of this integral, b to t f of x dx, provided the limit exists, right? So this one's just the same idea in the other direction, okay? Same idea, other direction. And then finally, oh yeah, we have to do we'll define this integral. If we want an infinite integral in both directions, then we simply split it in two. And then use the definitions because each of these pieces is defined above, right? So the basic idea here is if I've got some function that does this in both directions and I want all that area, I could just pick some letter A in the middle and do two integrals. One integral off to the negative side where I add up that area, another integral off to the positive side where I add up this area. And it doesn't matter where A is. You could pick 0, but you can pick any convenient number to split it, right? It still should add up to the total area if they exist. Again, either one of these might not exist, in which case the whole thing doesn't exist, okay? So those are our definitions, okay? So let's do two examples, and then we will look at that graph that I keep hiding from you, okay? We're gonna do two quick examples. I'll just leave the graphs up and then we'll talk about their relationship to this in just a moment. All right, so let's do the example. -1 to infinity. Actually, sorry, I'm changing my mind. Let's do it up next to our definitions so we can see precisely how we're applying the definitions. And then we'll look at the graph. So I'm gonna take this space back. Let's look at the integral from 1 to infinity of x to the -1 dx, right? So this is this example here. This is the type here where we're going from a number to infinity. And the definition says I take the limit as t goes to infinity of the integral from 1 to t of x to the -1 dx, right? So you don't have to put these here, but I like to. What I'm telling myself is I'm not thinking about the limit yet. There are two big things here to do: compute an integral and then take a limit. I don't want to think about both of them at once. So right now I'm just copying the limit without thinking. If you want to go and do this integral off to the side, that works too, and then bring it back in. So the antiderivative of x to the -1 is natural log absolute value of x, and we're evaluating it from 1 to t. Oops. I'm going to drop the absolute value since we're only looking at positive t anyways. We're starting at 1 and going to infinity. So this is the natural log of t minus the natural log of 1. Natural log of 1 is 0. So this is just the natural log of t. What does natural log do as we give it larger and larger inputs? It gets larger and larger. And so we write infinity to mean this function doesn't have a limit. The limit doesn't exist. The function, in fact, gets larger and larger and larger the higher the t values we put in, okay? Let's do one more, a very similar function, x to the -2 dx. Again, this is the same type. We're going to do the limit as t goes to infinity, 1 to t, x to the -2 dx. This is the limit as t goes to infinity. The antiderivative of this is -x to the -1, evaluated from 1 to t. Limit t goes to infinity. So this is going to be -t to the -1 plus 1 to the -1, right? There's a negative in there and we're subtracting it. What happens to, so this is really, let's use our limit laws, t to the, as t goes to infinity, -t over -1 plus the limit as t goes to infinity. 1 to the -1 is just 1. So the limit of a constant is just a constant. -t to the -1. This is 1 over t with a negative in front. T gets larger and larger. This goes to 0. We're left with just 1. And so this one, we say, has a finite area. In fact, its area is just 1. Whereas the one above does not have a finite area. Its area continues to grow without bound, right? Meaning we can make the area of this one as large as we want by taking t large enough. All right, so couple things. When we have this, if the limit doesn't exist, right? If we get to the provided the limit doesn't exist, well, let's say when it does exist, if the limit exists, we say the integral converges. Or we could say is convergent. The integral is convergent. Either one. Otherwise, if the limit doesn't exist, we say the integral diverges. Or we say it is divergent. So in these two cases, this first one diverges. This one converges. And in fact, it converges to 1. Okay, so a little extra vocabulary there. The other thing is, now let's finally look at these two graphs. So what I have graphed here is x to the negative 1 and x to the negative 2. In red, oops, I guess it won't let me draw on top. No. In red, I have x to the negative 1. In blue, I have x to the negative 2. Notice x to the negative 2 is smaller than x to the negative 1, right? That should make some intuitive sense. If it was larger on this interval, we would not expect its area to be smaller than the other one. So that's good. The other thing I want to point out, and I will prove this in another video, but I'll wait a little bit. I'm actually going to, and you should attempt to prove this on your own. This is a good exercise. It turns out this x to the negative 1 is kind of a division. And what I mean is this. Notice that each of these integrals that we just looked at had the following form. It was x to a negative number, right? And it turns out that we can make a rule around these, and we can say this kind of integral is convergent if p is greater than 1. Otherwise, it diverges, right? And we saw an example of that here. Here, from 1 to infinity of x to the negative 2 dx, the p-value is 2, which is greater than 1. In the first case, it was 1, which is not greater than 1. And so it diverged. And so if you ever see something like x to the negative 1/2 on this kind of integral, you know that it diverges, right? On the other hand, if it's x to the negative 3, you know that it converges. However, you don't know what it converges to necessarily, right? Here, here we see it converges to 1. It will work out differently, right, for different values. So you have to work through some of that. But at least you know it converges when you start. So if you make an error, you'll know that it's an error, knowing that it has to converge to something. All right, that's it for this one. I think we had enough there. I'll do some more examples. We'll talk about the other kind of improper integrals in some later videos. Thanks, everybody. See you next.